with we're calling what we did last time. So essentially prove monotone class theorem. Simply say that if you have an algebra, with an algebra, then the sigma field generated by the algebra is same as the monotone class generated by. This was essentially the last thing that we did. Why we prove this result? Because we want to use it. Okay. We have to prove something called Fubini theorem. So let's begin. Imagine you have two measure spaces, so x, y, and mu, x a and mu, and y b and mu. By b, I don't mean Oral sigma-algebra, just any sigma-algebra. We define, we constructed, what do we mean by sigma-algebra? You know that's a sigma-algebra generated by the algebra of all rectangles. Okay, so we constructed this sigma-algebra and then we constructed, you can call it a product sigma-algebra, and then we constructed a measure on this product sigma-algebra. That's the product of the measure mu and nu. We have to get a product measure. We can see as a map from 0 to plus infinity. In other words, we constructed this new product measure space actually using the existing measure spaces. And then we also felt that you can generalize it. Okay, so it's like you can generalize it up to, say for example, the finite number of products. So you can take, finite number of measure spaces, and you can construct a product measure algebra and product measure. Okay. For finite, there is no issue. But for infinite, if you want to define or if you want to take the countable number of measure spaces and you want to define their product sigma-algebra and the product measure, then it's non-trivial actually. So you can't just simply take any number of sigma-algebras and then construct product measurable, product sigma-algebra and product measure set. So with up to the finite things, inductively you can argue that you can construct or you can generalize it. Okay. So at the moment I'm going to assume that we have kind of constructed what is called finite dimensional finite dimensional Lebesgue measure, because if you take mu and a and b to be appropriate measure, then you can get finite dimensional Lebesgue measure as well. Okay, so the analysis that we're gonna do onwards is gonna be what? We're going to do it for the two product measure, but as I'm saying that you can inductively generalize it up to at least finite, number of spaces. Okay. What should be the next thing? The next thing, that So if you constructed this space, it kind of starts or begins, kind of give rise to a hell lot of new questions happen. For example, you can ask how to integrate in such kind of map, such kind of a space. Then so there's no difficulty in defining that what would be the integral, in this such kind of a measured space. But you can also ask a question that would that integral have a relationship with integral in this space and the integral in this space or not. We're going to see that there is a theorem called the Fubini theorem giving answers to all such questions. And we can also generalize Fubini theorem to the higher dimensions as well. Alright, so to begin with, what I'm going to do, so like this would be fixed notation. For me, F always is going to be a map from x cross y into zero to plus infinity, that is measurable with respect to this product sigma-algebra. And how I want to begin, I want to define. So previously I defined what is the meaning of a section of an element here actually. But now I want to define what is the meaning of a section of a measurable map. Previously we defined the section of a measurable set, now we define the section of a measurable map. So let me define a map as x. So in other words, for every x I can have, in x I can have such a map. That's going to be a map from y into 0 to plus infinity, defined as that if f actually is a section of f determined by x actually. Xf when operated onto y gives me f of xy for all y in y actually. So in other words, the section of a map is nothing, you just take the x and fix the first argument actually and keep the random function. Then I can see if the first argument is fixed, then I can see this as a map from y into 0 to plus infinity. So it's a section of a y. And similarly, I can also define what we call a section of f determined by every element y, that is going to be a map from x to 0 to plus infinity. So when this guy operated onto x will give me f of xy, where x is polynomial. So it's like y is fixed while the x is variable for all x. So I'm going to turn these two functions, which I'm going to use later quite often, as the sections of the function f. What is the natural question that you can ask about these functions? One of the natural questions that you can ask about these functions is that if f is measurable with respect to these product spaces, are these sections of f also measured? Let's check it. Let's do one thing. Let's say that for all x, if I have as x of f operated onto y is defined by f of x comma y for all y and y. For all y and y, then this Sx of f, which is the map from y to 0 plus infinity, is B measurable. So it's B measurable. Otherwise, I want to derive the measurability of this section from the measurability of Fn. In order to show this, what I need to do, I need to take a Borel set, okay, and consider the inverse image of the Borel set, okay, under this map. Okay. And then, I want to show that this inverse image belongs to the Borel sigma-algebra B. Therefore, we're going to say that like this map is mathematical. Okay. So by definition, what does this mean? This means that it's a collection of those y's from y such that F operated onto y is sitting in the Borel set B. Okay, by definition. So this means that if your y is in y, that means that f of xy belongs to this Borel set. And which also can be seen as that x comma y lives in this set f inverse of b. Okay. Now if B is a Borel set, what we can say about f inverse of B? Now since f is a measurable map, then this f inverse of B is an element in this product sigma-algebra. Okay? And so in other words, this is like a set E in the product sigma-algebra. So what can I say about this set? That this set is a collection of those y's such that xy is in V. So is in E actually. So I can say that this is nothing but it's a section of the set. Okay. F inverse of B. Okay, so that's a section of F inverse of B. Now, since F inverse of B is in E, F inverse of B is in E by definition, because F is Borel measurable, then we know, and we proved basically one of the first results in last discussion, that if you take an element from the Borel sigma-algebra and consider its section, okay, determined by X, then this section is gonna be in the Borel, not the Borel, but the sigma-algebra B. Okay. So we kind of showed what we want actually. And what does this shows? That this section of F is a B measurable, or calligraphic B measurable map. Okay. It's a calligraphic B measurable map. And you can similarly show that the other map, the other section, okay, is also an A measurable, calligraphic A measurable map. That you have written as Ty. Okay. So the next agenda is to prove an interesting theorem. Okay. Then I will write things about Fubini theorem. Should I give you an overall objective? Then I must write, because then you will see that why I am proving this theorem that I want. So what we just showed, that this section of F is a B measurable map actually. Okay. So if it is B measurable map, that means that I can integrate this guy. Okay, I can integrate this guy with respect to the map du actually. By the way, this guy is going to be a function of what, if I see this as a function?
Function of x.
So it's going to be a function of x, right? If you're integrating with respect to y, roughly integrate. This is going to be an expression in x. So in other words, I can see this as a map from x into, okay, 0 to plus infinity. I can see this as a map from 0 to plus infinity. Okay. So I'm going to show what? I'm going to show that this is measurable, and if this is measurable, a measurable actually, calligraphic a measurable, in the space x. So this means that I can also integrate it. Okay. So I just integrate this measurable map with respect to dv. So such an expression makes sense if this is a measurable. And then I would like to prove a key identity, okay, and that is going to be roughly, let's say the Fubini theorem, that if you have this, then this is equal to, okay, integral of the f with respect to the product the mu product. Okay, this is what that I'm gonna show actually. Okay, and interestingly, if I say, for example, go other way around actually. So in other words, I take this t by f. So I know that it's a measurable map. So I can integrate it with respect to mu. Then I can see this as a b measurable map, and then I can integrate it with respect to nu, okay? And since these guys, since such an equality holds, you also expect that this would be also equal to this. And hence, you also get equality between these iterated integrals. And if you see, this is nothing, this is just same as something that you have already learned in your calculus courses, that you can switch, what do you call the differentials, and you can change the order of integration. Okay. So this Fubini theorem, one of the consequences of Fubini theorem is that you get this change of order integration result very generalized in a generalized manner. So the only thing that you require is that make sure that the thing that you are integrating is measurable. That's it. Okay. Then you can switch like that. Anyway, so that's a rough sketch of Fubini's theorem. And if you see, we kind of already set the agenda. So we showed that this is measurable. Now we're going to show that this guy is a measurable. Okay. And this guy is a measurable. And then if you integrate it again, you're going to get this. So at least there are going to be 3 steps. Again. So that's what I would like to do. So let's move to the next step, in which I would like to move an interesting identity. I will do this, I'll try to do this very rigorously. Okay, the second part I will leave it to you, since you have to do it for yourself. Okay. I'll do one part rigorously. No gaps. So what I would like to show next, I would like to quickly prove theorem. Okay, with all previous notation, I would like to prove that these maps 2 facts. The map x into mu of the section of Fx of E, okay, here we mentioned that E is a measurable set in the product sigma-algebra, okay, is is A measurable. So this map is A measurable. And similarly, we can also show that mu. Are we happy that this expression makes sense? Because Sx of E is what? It's a set. It's a measurable set in the calligraphic V. So the expression makes sense.
It's a real.
So y of E is B measurable. This guy is B measurable. So that's the first part that I would like to prove. And the second part that I would like to prove is that if I integrate, okay, mu of this section, okay, of E with respect to mu. So if I integrate this mu of Sx of E, in other words, this map actually, obviously. So don't just see this as a number actually. Okay. Obviously, if you see it when it's in isolation, you're going to see this as a number. So what I'm saying is that if I take this map and I integrate it with respect to the mu, because it's mu measurable, this would be equal to, okay, the product measure mu of E. Okay. And similarly, I can also show that the mu of Ty of E, its integral with respect to mu is also equal to the same one. This is what the number is. And this would be a very helpful result theorem. How I'm going to show it? Okay, so this will be the second part. So how I'm going to show it? I will start this first part. Okay, let's do this and let's do the first part. So I'm going to do this first step or the first part in 3 steps. First, I will consider when E is a rectangle. Okay, this is true. Then I'll say that the E is a finite union. In other words, it's an element of calligraphic A cross calligraphic B algebra, not a sigma algebra. Okay. And then I'll try to prove this for the general case. Okay. This is what is my key. By the way, throughout this discussion, there is an also explicit assumption that this x and y are sigma finite. They are sigma finite. In other words, they can be written as an increasing sequence of sets with the finite measure. Okay. So this assumption is there. So consider the case, in other words, the case A, when E is a rectangle, in other words, A cross A. A is in calligraphic A and B is in calligraphic. And I want to show that this map is measurable. By the way, what is the section of E determined by any x in X? I know that this guy is equal to B if X is in A and it's empty. Okay. If X is in a complement. Okay? Alright? But that follows from the definition of section. If you haven't seen previous lecture, my sympathies are with you. Okay. Okay, so you have this. And once this is true, then I can say that the nu of this guy would be same as nu of B if x is an A,
Otherwise, 0.
and that would be 0 otherwise. Okay. And I can put these both things together and I can say that nu of Sx, the section of E determined by x, is basically nu of B multiplied by the indicator function A of x. Okay? Are we happy with this? Okay. Now, keep in view that what we wanted to show. We wanted to show that this map is immeasurable. Now I have said that I can write this expression explicitly in this manner. Keep in view that the A isn't the sigma-algebra A. Then what you can say about the indicator function? So if you have an indicator function of a measurable set, then what you can say about indicator function?
Measurable.
Must be measurable.
Measurable.
Indicator function of a measurable set is a measurable map. Okay, so this guy is measurable. And if you multiply a measurable function with a number, that's a number, it's still a measurable. In other words, this guy is measurable. Okay, this guy is measurable with respect to what? It's a measurable. So multiply by a number a measurable. So that's an a measurable. Okay. So this is a measurable. Is it making sense? So we proved the claim but for rectangles. Now let's take A from E from J cross B. Shouldn't be a difficult thing because this should easily analyze it. So now we need to show B. Okay. And 4. So the B is when A is in this algebra. Okay. So that's an algebra. That's a collection, so the algebra generated by all rectangle sections. So in other words, an abstract element here is a finite union of rectangle sections. Okay. So consider this case. So if this is the case, then E is basically a union of I equal to 1 to n EI, where each of them is a rectangle, and this each of these EIs I equal to 1 to n, you may assume without loss of generality that it's each of them is AI cross BI. Okay? Where AIs are from calligraphic A and BI is from calligraphic B. I'm not writing it, but it's obvious. So what should I do? I must do same what I did here. So consider the nu of the section of E. Okay. We also saw in the last lecture that if you consider the section of a union, then this is same as the union of the section section. So this would be I equal to 1 to n. Okay. Sx of EI. Okay. Sx of EIs, yes, this is going to be the case. And since mu is a measure, so I can write this guy is I equal to 1 to the n, indicate a function, okay? Okay. Mu of Sx of EI. Okay? This will be nu of Sx of EI. Where the EI is a rectangle actually.